Hello, everyone. My name is Dr. Vladimir Nekhendzy. I'm clinical professor of anesthesiology and otolaryngology at Stanford University Medical Center. Today, I'm going to share with you some of the exciting perspectives of the application of artificial intelligence and robotics to anesthesia practice, and specifically to the management of the difficult airway. I have a conflict of interest to disclose for this talk. I'm the founder of the Silicon Valley startup company Spiro Robotics, which is developing AI-powered robotic-assisted next-generation airway management devices. But I'm not going to be talking to you about the Spiro technology today. If you're interested to learn more, please feel free to contact me privately. My email will be listed on the last slide of my presentation. The purpose of my talk is rather broad. I want to give you a good overview of the subject. I'm going to introduce you to the role of AI and robotics in anesthesia. I'm going to make a case for the use of the AI-enabled robotic-assisted difficult airway management in the 21st century. I'm going to tell you about the current state of work that's been done to date by different researchers. We're going to discuss the ideal AI robotic tracheal intubation system. I'm going to give you a value proposition for such a system. And then at the end, I'm going to touch upon some of the future directions in this exciting field. In a recent excellent review of applicability of AI to clinical anesthesia, Hashimoto and colleagues have identified 6 promising areas. The first 3 relate to the intraoperative use of AI and smart automation, the so-called pharmacological robots, for controlling the anesthetic drug delivery systems by using the closed-loop monitoring and algorithms, and also for predicting significant intraoperative events, for example, the occurrence of intraoperative hypertension. The next 2 relate to the use of the actual mechanic robotical devices for better procedural precision, for example, for the placement of the peripheral nerve blocks. The last one refers to the use of the big data analytics to improve the logistics and efficiency of the operating room theater. So as you can see, notably, the use of AI and robotics for airway management is missing from this list, and for no good reasons, I would say. Because the patient's trachea needs to be intubated first. So all these exciting AI perioperative applications may take place at a later time. So what is the need for the AI robotics, for the use of the AI robotics for tracheal intubation? Do we really need it? And the answer to this question is the emphatic yes, and for the following reasons. So first of all, difficult tracheal intubation is a real problem. At least approximately 2.5 million difficult intubations happen annually in the United States. The majority occur in the operating room and the smaller number in the ICU and emergency department. 30 million intubations annually are performed, 2.5 million of those difficult, and they inflict significant patient suffering, patients' injuries, and also substantial loss to the hospitals. The patient's injuries range from moderate to severe damage, from the broken teeth, mucosal lacerations, to significant upper airway edema as a result of the multiple intubating attempts. And not a small number of patients end up dying or sustaining permanent brain damage as a result of the repeated intubating attempts, which lead to hypoxia, cardiac arrest. The cost of each difficult tracheal intubation episode is approximately $11,000, and this is not even counting the cost for taking care of these patients who had sustained permanent brain damage. In addition, there is a lost revenue due to canceled surgeries, higher costs for readmissions and the lawsuit, and the average lawsuit payment, according to the ASA closed claims, is about $250,000. Second of all, even best video techniques that we use for difficult intubation, such as video laryngoscopy and the flexible intubation scope, have their limitations. And this is because each tracheal intubation step involves three steps, three critical steps. First, you have to visualize the anatomy. You need to understand what you're looking at. Second, you need to navigate your endotracheal tube towards that anatomical target. And three, you finally have to place physical act of placement of the endotracheal tube through the vocal cords and into the patient's trachea. And the problems can occur at each and every step. And if they occur at all the steps, then we are dealing with very, very difficult tracheal intubation or even the intubation failure. Unfortunately, none of the techniques can improve all three steps that are required for successful difficult tracheal intubation. For example, the video laryngoscopy provides outstanding visualization. However, there is a problem usually with navigating the endotracheal tube towards the target, as you may be able to appreciate from this video. In addition, the placement of the tube frequently requires corkscrewing the tube in, with the possibility of the vocal cord trauma. The flexible intubation scope, on the other hand, provides excellent navigation, excellent maneuverability, and facilitates the tube placement. However, there is a problem with visualization because the camera is close up, no panoramic view. And also, the visualization is going to be very easily obscured by blood and secretions, while with video laryngoscopy, it's a much more resistant technique. In addition, this technique is very difficult to learn, which accounts for its relatively infrequent use in difficult airway situations. Moreover, the limitations of the video-assisted techniques become even more evident when you consider the critical importance of the success rate on the first intubating attempt, because the patient's damage increases exponentially with each intubation attempt, leading, again, to major airway trauma, emergency surgical airway, cardiac arrest, and hypoxic brain damage. The high first pass success rate is really the goal to reduce the risk. And if you look at the data which I compiled from different studies, the best rate for the video laryngoscopy, and that's the first technique which the people use when faced with difficult situation, is nowhere near 100% in the best controlled conditions in the operating room. It's around 92% only. And then you move outside of the operating room to emergency department and intensive care unit, you're going to be hovering around 80% on the first pass success rate only. With a flexible intubation scope, it's even less. And also there are special vulnerable patients populations in whom both these techniques are going to fail very frequently. Like, for example, the pediatric patients, the morbidly obese patients, the patients with oropharyngeal cancer, and so on and so forth. Finally, only being human is another good reason to have an intelligent assistant by your side. This assistant never gets tired and can improve your skill in the high acuity situations. In difficult airway situations, we are faced with a complex decision making. This decision making has to be done quickly. It's inconsistent because the difficult airway scenarios are multiple and they're completely different from one another. We frequently have time constraints and production pressure when dealing with a difficult airway. If this is combined with not good anesthesiologist-surgeon professional interactions and relationships, that will impact negatively our preparation and management of the difficult airway. Fatigue and sleep deprivation impair the cognition, as well as stress, and decrease the quality of the necessary preparations required to be prepared while dealing with the difficult airway. We need to have all the devices ready to go on the fly. Finally, under stress, what happens that we frequently revert to heuristic approach, the so-called cognitive shortcuts, which leads to bias and suboptimal patient care. The anesthesiologists also possess different dexterity. Some are good, some are not so good with different airway devices and techniques. Some may not have used the flexible intubation scope for years. And the experience and judgment are highly individual. As the good saying goes, good judgment comes from experience, but experience comes from bad judgment. Unfortunately true, and all this leads to errors and preventable harm to the patient. So where do we stand? What's been accomplished today? The first report on robotic-assisted intubation, and I actually had the pleasure and privilege to be one of the reviewers of this report, was published a decade ago. And the authors used they actually hooked up the regular Da Vinci robot to the flexible scope and used this flexible scope to intubate the mannequin, both orally and nasally. The robot was manipulated in the usual way through the surgical console, and the mannequin could be intubated by either route in under 70 seconds without any significant problems. The first use of the robotic intubation in human patients was reported by Hammerling in 2012, the so-called Kepler intubation system, which consisted of the gaming console, actually with a joystick, Pentax video laryngoscope, and the software that interfaced the joystick with the actual operation of the Pentax. They studied 12 patients. The intubation was successful in 11, giving 91% success rate. The failure was related not to the use of the robot per se, but to the fogging of the Pentax video laryngoscopy lens. The intubation was accomplished in about 60 seconds in these settings. These reports were followed by other investigations aimed at finding optimal designs for robotic intubation interface in the laboratory setting. In parallel, the efforts have been made to use the machine learning for predicting the ease of intubation in real patients. For example, Conner and Siegel in these two publications developed a computer model for predicting intubation difficulty based on the analysis of the photographs of patients' faces. Their predictive algorithm demonstrated 87% accuracy, in contrast to 58% predictive accuracy of using the Mallampati score and thyromental distance. Quindet and colleagues in 2016 developed an automated face analysis machine learning algorithm to detect morphological features that were associated with the difficult intubations. They used the database of approximately 1,000 videos and photographs, and the positive predictive value was not very high, unfortunately, less than 80%, 78 to be exact. The automation of such decisions became possible by the implementation, just in case you were wondering, of the deep learning machine algorithms that employ multiple hidden layers of artificial neural networks. These neural networks are basically the digital equivalent to our biological nervous system. The input and hidden layers contain thousands of nodes. You can think about it as neurons. All the activations of the neurons in the first hidden layer are fed into each of the individual neurons in the second layer, and then subsequently to the third layer and fourth layer, and so on and so forth, providing the huge amount of information. The final logistic output is hopefully going to be a correct decision making And in terms of the difficult airway, predicting easy mask ventilation, difficult mask ventilation, or the easy or difficult intubation as being investigated by Matava and colleagues at the moment. Of course, the experienced clinician whose native biological neural networks are already deep enough may not need such computer-generated help. In fact, if you, all of you, look at these photographs of the patients, you will probably understand very quickly that none of them has a difficult airway, right? But what if I told you that none of these subjects actually exist? That they are all the computer-generated, AI-generated images, a fantasy, if you will. This is the example of what AI can do for you, or can do for us. This is the example where the advanced AI applications can actually get a little spooky. Then 2020 was a really breakthrough year in the use of AI and robotics for airway procedures. Matava and colleagues developed a machine vision algorithm that could detect, classify, and label the vocal cords and tracheal anatomy in real patients and in real time. The algorithm worked the way that it would display the target with a probability, giving the probability of the correct identification. The vocal cords could be identified as well as the tracheal rings. This is the pediatric patients breathing spontaneously. Matava is the pediatric anesthesiologist out of Toronto. The algorithm could identify the vocal cords and trachea with high sensitivity, 87% and almost 100% specificity. Biro and colleagues, Peter Biro from University of Zurich in Switzerland, brought this concept of smart intubation using airway recognition to another level. In a mannequin study, Peter was able to demonstrate that based on correct anatomical recognition, the AI can also command the robotic interface, here represented by the rigid video stylet, to automatically, the AI was able to automatically navigate the stylet into the mannequin's trachea. Moreover, this device was significantly different from all others because it had an aspiration of being portable. It's still pretty big. You know, it was a conceptual prototype, but nevertheless, that was a giant step forward, a landmark study in a way, which showed us that the future use of smart navigation in the new generation of robotic-assisted airway management devices is possible. So what would be the ideal AI robotic tracheal intubation system? None of such systems currently exist clinically. Well, it obviously cannot be any of these. They are too bulky, they are unfriendly, they cannot be used. So here are the requirements as I see them. First of all, it has to be obviously the video-enabled device. It could be the video laryngoscope, it could be the flexible endoscope, it could be the rigid endoscope. It has to provide continuous video stream of good quality with instant feedback to the operator. It has to have real-time or near real-time processing speed, and it has to provide a reliable AI image recognition and targeting. From the operational perspective, it has to be portable, it has to be handheld, it has to be operated only by a single person. One operator use, single device. It has to be easy to learn and use, highly usable device. Everything, all the components must be assembled on the fly. No complexity must exist. It has to have the manual modes that will allow the operator to override the AI manipulations, manual assist and override modes, for example. And finally, it should have the backup options if AI and robotics fail. So not an easy task for creating such a device. In addition, From the purely marketing and business point of view, this device better have universal appeal. It so it can be used in both adult and pediatric patients. The same device. It can be used for awake and asleep intubation, can be used for oral and nasal intubation, can be used for other techniques that we employ in the management of the difficult airway, such as, for example, the intubation through the supraglottic airway devices. And finally, if we want to bring this device outside of the operating room, it has to be highly usable by paramedics, emergency department, and the ICU, for example, for the endotracheal tube exchange. So here is the value proposition for the use of the AI-enabled robotic-assisted tracheal intubation devices. So first of all, there will be some applications for predicting difficulty and for airway monitoring. But in terms of the tracheal intubation per se, these devices can improve all critical steps: visualization, navigation, and tube delivery with precision, near geometric precision, in fact, which will result in the increased first pass success rate. And finally, and very importantly, these devices will enhance the skill level of the operators and reduce the variability of care. This was actually the original appeal of the robotic systems, that they will level the playing field, if you will. They will allow the not so good surgeon to become a much better surgeon. And they will allow the excellent surgeon to become the master of the universe, if you will. The same for the anesthesiologist. With these systems, I cannot make the bad operator excellent operator, but I can make the operator a decent operator. So the patients will not suffer. And I can make the excellent operator an outstanding operator. And we can reduce the airway trauma, reduce the hospital cost, and improve the overall patient safety. So where are we? What does the future hold for such devices? We don't know. We don't know. Because we are right here. If you look at this technology hype cycle, we're right in the beginning. And hopefully very soon we're going to be approaching this peak of inflated expectations. There is long road for us to go with disappointments and trials and errors until we hit the slope of enlightenment and plateau of productivity, when we finally figure out how to build these devices so they work effectively, reliably, and provide what they're supposed to deliver in multiple difficult airway situations. One thing is certain, though, that the development of such technology is a natural progression of technological advancement of the 21st century and will lead to vastly improved patient safety. And with this, I wish to conclude my presentation. I do hope that you will share with me the excitement of the transformational tracheal intubation technology that we will see in our hands in the not so distant future. I want to thank the organizers of the Congress for inviting me to speak. And I also want to thank you for listening. Please stay safe and healthy. Thank you very much.